Okay, I want to review what we started from synthesis of arachidonic acid. I mean prostaglandin biosynthesis. So we want to, I mean, review all of it once again, but with a larger screen. All right. So first, I'll start by discussing the synthesis of arachidonic acid from linoleic acid, which is seen from plant derivatives. Linoleic acid is an octadec an octadec deca dienoic acid, specifically an octadeca 912 dienoic acid with a structure that looks kind of like this. Since it's 18 octadeca, so it's 18 carbon. So we count, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is the basic structure of linoleic acid. So if you count the number of carbons, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So from carbon 9, 10, 11, 12. So this is the basic structure of linoleic acid. It has double bonds in carbons 9 and 12. Now, I want to talk about the synthesis of arachidonic acid from linoleic acid. So we said it involves a two-step reaction. First, there's going to be desaturation, and then there will be elongation. So this 18 carbon compound will eventually become a 20 carbon compound. So the first thing that happens first is that there's going to be desaturation of linoleic acid. There will be desaturation of linoleic acid at the carbon 6 position. At the 6th position from the carboxylic group. So if we count from the carboxylic group at the 6th position, if this is 3, 4, 5, 6, so there's going to be desaturation. That means this hydrogen here and this hydrogen here, this hydrogen here and this hydrogen here will be lost in the presence of the enzyme desaturase. So the enzyme catalyzing this reaction is a desaturase enzyme. So this desaturase enzyme makes use of NAD plus to abstract two protons here. So we get NAD plus, NADH and H plus. So we started from linoleic acid, which is an 18 carbon acid with two double bonds, one on carbon 6 and the other on one on carbon 9 and the other on carbon 12. But now due to desaturation, due to removal of two protons from carbon 6 and carbon 7, now we have a new fatty acid, a new 18 carbon fatty acid that has 3 unsaturations. So if you count, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is 1, 2, 3, 4, 5, 6, 6. Now there's an unsaturation on 6. There's an unsaturation on 9. And there's an unsaturation on carbon 12. So this is a new organic compound now, which is having 3 double bonds now. 3 double bonds which are seen on carbon 6, 9 and 12. So this is no longer the regular linoleic acid. This is our regular linoleic acid, but this is called gamma linoleic acid. So gamma linoleic acid is an 18 carbon carboxylic acid with 3 unsaturations from the position 6, 9 and 12. So this gamma linoleic acid will then be elongated due to the addition of 2 carbons from malonyl-CoA. Malonyl-CoA is a 3 carbon organic compound that is attached to coenzyme A. So malonyl-CoA, let me write the name here, it's 3 carbon, just like I said. Malonyl-CoA we donate 2 carbon from this 3 carbon, right? 2 carbons will be donated to malonyl-CoA and 1 carbon will be lost. So 1 carbon will be lost in the form of carbon dioxide. You should check out the structure of malonyl-CoA for better clarity. So now that we've got 2 carbons donated here, 2 carbons coming here, these 2 carbons are attached to our 18 carbon gamma linoleic acid, so to give a 20 carbon organic compound which is called dihomogamma linoleic acid. So dihomogamma linoleic acid is a 20 carbon compound, so which has the structure we count this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now because of the addition of 2 carbon, because we are adding 2 carbon to this compound, so because of the addition of 2 carbon, the position of the unsaturation is going to change. So imagine addition of 2 to the position of the double bond. So the position of the double bond shifts from 6 now to 8 with the addition of 2 carbon. So we have our first unsaturation on carbon 8. This is 1, 2, 3, 4, 5, 6, 7, 8. So we have our first unsaturation on 8. The next unsaturation will be on 11, that's 9 plus 2, 11. This is 9, 10, 11. So the next unsaturation will be on carbon 11, and then the next, this is 12, 13, 14. The next unsaturation will be on carbon 14. So this compound here, which is a 20 carbon organic compound bearing unsaturations from 8, 11 and 14. This compound is called dihomogamma linoleic acid. So these are dihomogamma linoleic acid, and this dihomogamma linoleic acid will eventually undergo desaturation on the position on the 5th position. So on carbon 5, there's going to be a desaturation on carbon 5 for us to get our arachidonic acid. So the enzyme catalyzing this is definitely a desaturase enzyme. So if we look at the first step here, the desaturase enzyme was acting on carbon 6, was removing 2 hydrogens on carbon 6. But in this case now, the desaturase enzyme is removing 2 hydrogens from carbons 5 and carbon 6. This one is carbon 6 and 7, so here we have our desaturase. Our desaturase acting on carbons position 5 and 6, so specifically positions 5. Okay. Okay, so after desaturating diamogamma linoleic acid on the position 5, we now have a tetra, like 4 double bonds being formed now. So we have a double bond on carbon 5, a double bond on carbon 8, a double bond on carbon 11, and a double bond on carbon 14. So we have an eicosanoid, that's a 20 carbon compound formed, which is specifically called arachidonic acid. So let's draw 20 carbon, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So these are 20 carbon organic compound. So we now have our unsaturation from carbon 5. So there's an unsaturation here, carbon 5. So there's an unsaturation on carbon 8. There's an unsaturation on 11. And there's an unsaturation on 14. So the enzyme catalyzing this reaction is the desaturase enzyme. The desaturase enzyme. And of course, it's employing the use of NAD to abstract 2 protons, one in the formation of NADH, and then one free proton will be released. So this compound formed is our arachidonic acid, which is the primary precursor for the biosynthesis of prostanoids. Now the next step, the next thing that occurs is going to be the fusion of this arachidonic acid with membrane phospholipid. So like we said, the membrane phospholipid can either be phosphatidyl serine, or it could be phosphatidylcholine, or phosphatidyl inositol, or it could be phosphatidyl ethanolamine. Anyway, for simplicity, I'd like to pick phosphatidyl serine due to the structure. So what happens is that arachidonic acid is going to fuse with phosphatidylcholine, so it will stay bound in the membrane phospholipid until when it is required for biosynthesis of prostanoids or lipoxygens or leukotrienes. So the next encounter, we are going to look at the process of fusion of arachidonic acid with the membrane phospholipid. So thank you.